Okay, so as promised, here is a bit more about network modeling. When we are thinking about structural modeling, we'll next move on to functional modeling. For some reason, even the original publication diagram figure is a little fuzzy in this nice paper. But anyways, we have looked at this before. This is the Earth system, so it's the entire kitchen caboodle of the human environment system that we talked about. And now you can see that there are many boxes as opposed to Venn diagrams, which had a different kind of arrangement like this. So here you have more like a piping diagram with the links between them, so it's more like a networking diagram. So you have here forcing, which is an external input of energy into the Earth system, and we split it into the human system here, which is the anthroposphere, but obviously technically speaking we are part of the big Earth system, which is the bigger box. Volcanoes are also an external forcing. As we said before, the definition of forcing, don't even have to say external forcing. Forcing is something that perturbs the energy balance at the top of the atmosphere, which is what you are trying to represent here. So volcanoes are also removing stuff from within the Earth which are not directly interacting with the climate system and putting it into the atmosphere, making it part of the climate system and the Earth system, because volcanic eruptions affect not only sunlight but also crop yields and human responses and so on. And you have fossil fuels which have now become part of the external forcing. Like volcanoes, fossil fuels are now coming out of the ground where they are not directly interacting with the climate system and being burned and being made part of the climate system. Of course, we are doing that as human beings, so that's part of the anthroposphere as opposed to the geosphere. So we said now geosphere and anthroposphere are not so independent, because as we saw with the picture of a mountain and human settlement on the slopes, we are now modifying things that are there. Mountains are there, geologically created by geologic processes, plate tectonics, but we are modifying them in terms of directly in terms of land use for building homes, but also indirectly by changing the rainfall pattern and creating landslides or changing vegetation and so on and so forth. Ecosystems are changing as well in terms of, let's say, mosquitoes moving up or butterflies and pollinators not moving up enough and so on and so forth. So main thing here is you don't get an idea of the spatial extent of these things, right? So we have geosphere and anthroposphere as two boxes, but are they the same spatial extent? Well, human beings are occupying most of the planet and influencing most of the planet, but we don't live in large numbers in the middle of the ocean. Antarctica we have colonized, but not in such large numbers as on land, and so on. So we have the cryosphere, stratosphere and troposphere, and the box sizes are relatively unimportant because we are not representing the spatial extent. So we are looking here at the interaction between stratosphere and troposphere and cryosphere and this atmospheric part, and the two-way arrows means stratosphere can affect the troposphere and troposphere can affect the stratosphere, and this system then interacts with the cryosphere. So you can see the geosphere, biosphere is in green, resource extraction is in this are in these green arrows, and then there are climate impacts being shown in different ways, and psychosocial feedbacks. We'll look at a bit more detail of this in a minute. So you have here psychosocial feedbacks in terms of the impact of the geosphere and the biosphere through extinctions and biosphere degradation here, and you have here the impacts on the anthroposphere from the geosphere via climate change. So distinction is made between biosphere and geosphere. As we said about things that are standing are not directly functional, like a mountain that's standing there. It affects circulation, rainfall, etc., but it's not actively functional in other ways, such as the troposphere, which can create clouds, water vapor, clouds, rain, cyclones, hurricanes, and so on. Stratosphere, of course, is important for the ozone and so on. Then the ocean, it's divided into upper ocean, lower ocean, coastal zone, freshwater system is interacting, and vegetation and roots and soils, and they are interacting with the lithosphere in terms of nutrient cycling, erosion, and so on. And all these things are sitting here in the biosphere, and you have pollution going back and forth here, and all of these are interacting with the anthroposphere in terms of resource extractions, both from the biosphere and the lithosphere. So you are extracting oil, gas, and so on, and you are having your energy systems, knowledge, science, technology, institutions, political economy, human populations, cultures, values, beliefs. And here, of course, you have production and consumption. Why am I reading this? Because this is a network diagram. Plus, we talked about agent-based modeling. So depending on how you want to represent this in a more spatially explicit manner, you are going to represent these human populations and institutions and political economy and so on as either boxes or agents. And of course, you have extraction and burial. So we grow crops, consume, and put stuff back into the earth in landfills, or as compostable matter, or in forests there is composting going on naturally, etc. So you get the idea that you have all kinds of links, and the results of this can also be represented in terms of nodes and links. So here you can think of these as nodes and connectivities, but you are not getting a sense of how strong are the connections between these, let's say, versus these here. So when people represent specific systems, let's say like a river system used for irrigation with humans and agriculture, then you can make a network diagram which shows the strength of the link from rainfall to river, river to irrigation, irrigation to crops, and so on and so forth. So I won't show an example, but you can see somewhat of an example in the same context as the Earth system here, but now it has a bit more details of connecting our dots. So you have socio-cultural taxon here, and you have socio-metabolic taxon and biophysical taxon. So this is a Venn diagram, essential Venn diagram that we talked about, where the ellipse of the CUL is interacting with ENV and creating MET, which is the social metabolic taxon. So you can think of it as what we grow and what we consume, and the businesses, the metabolism of the commercial exchanges, businesses, and so on. And you see the network diagram here now. So you have different sized, different thicknesses of arrows connecting to individuals, social systems. So now you have nodes and links here. This is not very systematic in terms of the thicknesses and distances, but you can see that now we are being more spatially explicit as well in terms of this representation. So you have a processes taxa here, entity types, you can think of these elements in our lingo in this book, and modeling approaches. You have agent based modeling here, so you are representing different, you can think of this as an agent, this as an agent, this as an agent, and so on. So you get different connectivities. So this is one way of modeling representing taxa. It is about entities, sorry, so these are the components, elements, and this are the modeling types. So adaptive network modeling, where as the system changes, let's say with global warming or shifts in populations or shifts in agriculture, deforestation, urbanization, you can have network where the nodes and the connectivities actually evolve. They are not fixed and stationary. Okay, and the relations in that sense also between individuals and social systems, which are political, economic, administrative, cultural, and so on. Or you also have difference equations where you are discretizing the system, so you can think of it as a numerical representation of the Earth system that we are talking about here, which are all the typical general circulation models used for IPCC simulations and projections. or you have differential equations, which is a first principle. We solve Navier-Stokes equations to solve the climate system. I have a whole course on climate modeling if you want to look those up, but typically those equations are very non-linear, so we cannot solve them analytically, so we end up writing them as difference equations as well. Or you sometimes have algebraic equations. A lot of times hydrological models may end up being written as algebraic equations or agent yeah, let's not confuse too much. And you have stochastic events kind of representation. So this diagram is a bit too schematic, but this gives you a good sense of what we mean by network modeling, where individuals are represented. These may be groups, communities, or towns that are interacting, or they can be actual individuals representing different regions. Okay, so it depends on whether these are actual individuals or communities being represented as individuals. Then there may be social systems that are overlapping in some ways, but they are distinct in the sense European culture is quite different than, let's say, Asian culture, but within the Asian culture also you have Chinese culture versus, let's say, South Asian cultures, which are much more closely related than to the Chinese culture via languages and other things and so on. So you get the sense of how modeling can be done, and you are here mixing the physical modeling with social cultural system modeling as well as biosphere modeling, which is what is implied here as well. So the details really matter in terms of what you are capturing, whether you are only doing the physical climate or also including biogeochemistry with carbon cycle, and again whether the biosphere is being represented as a fixed distribution of crop areas, forest areas, grasslands, deserts, or if they are evolving in space and time, and so on and so forth. So that's the brief explanation of how the details work. Okay, so let me, I hope I didn't misplace anything. Yeah, so network diagramming, let's read this a bit. Many central aspects of risk, resilience, and sustainability are spatial in the sense of being associated with geographical locations, which is what I indicated here. There are again many different tools developed to explicitly include such features in the construction of human environment systems, here categorized as different forms of mapping. Mapping is about generating visual representations of observations using spatial relationships, which is obvious here. It includes the practice of producing scale representations of geographical features, such as the maps of traditional cartography, but it's not limited to that. It spans from participatory mapping to high-tech geospatial data collection, such as LiDAR, which is a remote sensing technology illuminating a target with laser and analyzing the reflected light. So you could be looking at elevation changes, vegetation changes, and so on and so forth. So mapping is thus, in this context, a broad term that encompasses all spatial organization of information concerning human environment systems, using a wide range of symbolic representations from drawings to standardized map legends. Many tools have been developed over the years to guide various forms of mapping. Ground and sketch mapping are two examples of participatory mapping tools that plot maps from the memory of involved community members. And geographical information systems have opened up unprecedented opportunities for analyzing and visualizing geospatial information. That's about structural models. We'll come back and read about functional models. We are being very brief here, but as I said, I have more details on just climate modeling and a little bit about Earth system modeling in my climate modeling course introduction that you can look up, but there are also lots of very nice reviews, books, papers, and so on. So in this context, we will move on with this much detail for now, and we will keep coming back to risks, resilience, and sustainability. Okay.